So in the last lecture what we have seen actually like how the differential wheel drive can be incorporated with the line of sight and polar coordinate. So now in this lecture we will see that what we have done in the last lecture, that we will try to incorporate in MATLAB and try to simulate how that will work. Okay. So in the sense we will take a differential wheel drive and we will do both set point and as well as tracking with position tracking, or we can see like how to do the orientation tracking. So with that we will move to the MATLAB window now and we will take the earlier model and we will try to understand how to incorporate the you call polar coordinate or line of sight. So now we can actually like come back to the you can say the MATLAB window where I have already written the code for line of sight for a differential wheel drive. So you can see that I will actually like explain. So we have actually like taken Ku and Kr for the polar coordinate, otherwise we will directly take as a K, and these are the what you call the vehicle parameters, where the A is the radius of the wheel and you can see that this is the initial condition and these are the simulation parameter. So let us move what we have done. So what we have done is actually like there are two things we have done. So one is actually like we have calculated the rho, okay. So the other one is we are calculating the error. So the error is actually like based on the line of sight. So first we will see the line of sight directly. So where we will incorporate only E. So E is actually like eta tilde. So the eta tilde would be actually like calculating based on the line of sight. So where the eta desired would be compared with eta, but the angle which is what you call desired angle is actually like modified as new change. So that angle is actually like tan inverse of that, if you recall here. So here if you recall, this is what the psi desired. So the same angle we are actually like incorporating here. So that is what we have taken, and why it is actually like 2 argument tan inverse you know already based on the quadrant choice. So now this is what the error. So now this error is actually like it's a smaller range, in the sense I am calculating the rho. So from the starting to the end point, if the rho is keep on reducing, if the rho is actually like within 5 centimeter circle, so then I am moving to the what you call the orientation follow. Otherwise I will actually like keep it as simple position following or position tracking. So that is what the whole idea. So I will actually like come back. So now I will actually like make it this pass command. So now what we are doing the same thing. So we are taking as a zeta. Zeta is actually like inverse of, this is actually like position set point tracking. So you would not be having eta desired dot. So that's why directly we have written here. So and we are assuming that the K1 and K2 is actually like 2 each, in the sense Kx and Ky or lambda x, lambda y is 2 each, and lambda psi is 4. And now I have actually like taken, I already told right, the V is 0, right. So that's why V, U and R only there, and then we are actually like incorporating the wheel configuration and then we are actually like doing it. So that wheel configuration I have written already in the matrix format, okay. So this matrix what you have obtained here, right. So you can recall this is cos psi, sin psi 0, 0, 0, 1, right. So the same thing I have actually like incorporated here, you can see. So cos psi you can see sin psi 0 and 0, 0 and 1. So that is what we have actually like incorporated. So now if I run this, so what you can expect, so this will actually like follow something. So this particularly we have tried to record it. So now we no need to record that. So I am just making it that. So then there is no recording at all. So I am just making it this as. You will write position control. So now what you can actually expect, this is the differential wheel drive that is actually trying to follow the position which is the goal point, and after this you can say within that circle, if it is entered within the 5 centimeter circle, it is trying to follow the orientation. So that is what you would have actually seen. Again I am running that. So I will actually like show the maximize. You can see this is the starting point and it is trying to follow, and it supposed to come here. It is not a, you can say, position tracking, it is just a position following. So this is the given point and this is the final point, and you can see that within that circle it reached, it is trying to follow the orientation also, okay. So that is what I have actually like given as a code. So now you don't want that, you can actually like make it that also like comment. So I am just making it that as a comment. So now what you can actually see that it would try to converge to that given point. So without following the orientation, you can see the difference, right? So but what one can see, once it is coming to one particular profile, you can see that the vehicle is start over, you can say rotating. Why it is so? Because you can say the control activity is actually like giving preference to both. Okay. So because your side is actually like become almost 0, but you are trying to follow that, and as well as you are trying to follow your position profile. So this is one you have to actually like understand. So now if I give probably a positional coordinate as a polar coordinate, how that would work? So for that also I will actually like take another file which I have already written. So I will actually like take that. Okay. So here you can see that the u and r. So I am actually like taking as a polar coordinate. So and then I am actually like trying to control that. So and this is also like same thing. So it's also line of sight. I just see that particular file. So now you can see that this is what we have given, right? So only thing here, the sign is actually like interchange, the KU sign. Why it is so? Because you want to actually like reduce it. Now the error is actually like rho. You are trying to reduce the error. So in the sense you have to rewrite the entire equation in the other form. So then the KU would be positive. So if you recall this particular, you can say equation. So you can see this equation. So this equation u is actually like we have written as minus k rho into rho, but what we are actually like seeing, this rho is actually like a positive, but what we are interested, so this point actually like supposed to reach from here, so it is in the opposite direction, so that is why there is a negative sign coming into here. Okay. So in the sense u I have written as minus ku into zeta, but right now I put ku into zeta. You can actually like run the simulation and you will get your own idea. Now I am actually like giving the eta decide also like some kind of circular path. So in that sense eta decide dot also coming. So if I run this, so what one can actually like see it is actually trying to follow a circular path. You can see, right? But if I give a orientation component, it may not follow. So for that you can actually like see, so although I have given 0.1 times of t as like this, but if I give probably pi by 4 and all, it may not actually like follow. So in order to get that, so I will actually like give that also here. So then we will actually like take the other you can say configurations. So you can see here, so I am taking this 2 and I am trying to use this what you call polar coordinate form. So now if I actually run this, you can see it is actually like going the set point which is 1 by 1 and pi by 4, and I have actually like changed the condition here, the rho is actually like up to 10 centimeter, you follow only line following, after that you try to follow as a orientation. So that is what it is actually like doing it. So you can see like it start from 0 0 and try to go 1 and 1, and it is actually like trying to reach, once that circle of 10 centimeter reach, it is trying to follow the orientation, but both are not directly controllable, that is why there is a compromise between the position and orientation. Now you got it like what is non-holonomic vehicle, where you can apply, right? If you are actually like thinking about position tracking, it is actually like working well, but if you are thinking about orientation also need to be controlled, then it cannot be done in, you can say, non-holonomic conditions. So this is what the other case what I have shown as a circular profile following, where this dotted circle is the given circular profile and this particular vehicle is actually like asked to follow, it is doing it. So now you can actually like vary the control gain value. For example, I am giving very slow control in the x axis, you can say. So you can see, right. So the error is actually like prolonged and it is actually like not, you can say, controlled. Why? Because the steady state error is still exists. So if I actually like increase this probably into 5, it would be faster, right. So like that you can actually like see it, and when you go to error profile, so you can see that the error would be fastly converged to 0. So these all you can actually like see it. So this is one side where the differential wheel vehicle are coming into a picture. Now similar way you can see there are several non-holonomic vehicles are available, right. So one such vehicle is car like robot, where there are 4 wheels, but all the 4 wheels are actually like not independently controlled. So there are 2 wheels are actually like in single axle. So in that sense, in that one particular axle would be controlled with the traction, and the same wheel can be steerable or vice versa. Okay. In that sense, what I can do, I can actually take it that car scenario where the forward wheel drive line of sight method I am taking. So now you can see that the W matrix would get changed, so that you can actually like recall what we did in the what you call in our generalized wheel model. So this is what we have done, that you can apply and then get it. So now what you need to have, so you need to have actually like 2 things, one is steering angle, so the other one is actually like you call the forward velocity. So both we are trying to calculate based on the line of sight method, so where U and R would be calculated. So after that I will substitute in the W relation, and then I will actually like calculate what is your, you call the angular velocity of the individual wheels, okay, individual wheel and as well as the case. First I will run the simulation, then I will explain. So you can see here, so this is the forward wheel, so these two are powered in a single axle, and this is the set point as given, and it is actually trying to follow as a car, what you have done, right. So now you can see that this is what we are actually like interested. This is also non-holonomic, but here you can see that it is actually like forward wheel, in the sense that both you can say forward wheel is actually like powered in a single axle and as well as steerable. The same thing we can actually like do it for what you call the rear wheel drive. So this is actually like rear wheel drive, then you can see that the W matrix slightly modified where you compare to the forward wheel drive, okay, there would be tan phi would come. So I know like you know by this time, so how to derive this what you call generalized wheel model, how to obtain this W for forward and rear. So assuming that these two are available, and now you can actually get it. So the same situation I have given, but it is actually like the front wheel is actually steering connected and the rear wheel is actually like powered. So now this is actually like trying to you call follow it. So we will actually like see, this is actually like taking time, okay. So I will actually like, okay, so these are there, so I do not want to actually like record it. So this is actually like what you call video recording, so that is not supposed to be recorded here. So I will just run this and we can actually like see it, so how this will go. So you can see, right, so it is actually like taking a similar way, but only thing it is actually like slight variation would be in the control input, because it is actually like rear wheel drive. The similar way you can even go with you can say cycle, where only one wheel that would be connected with a few casters on the wheelbase, so that it can move it. In fact, in the last to last lecture I was discussed about this, so we can see that. So for that I am actually taking that another one, which is what you call unicycle model. So I will actually like take it that unicycle. So you can see in this case only the W would be having actually like one input. So where U and R is directly controllable. So that is what we are actually trying to take. So in the sense this is a unicycle, I did not show the what you call the passive caster wheels. So now you can see that this particular wheel configuration is trying to follow this. So I have actually like changed that configuration. So here also we record it, because this particular case we are using it for some other benefit, because we can record this video. So now you can see the same scenario, only thing it is actually like there is no restriction on what you call sliding, okay. So it is actually like still non-holonomic, but the lateral resistance is not there. So this is unicycle. So similarly only one left we did not discuss, that is the tricycle. I will take the tricycle also here and I will actually like run that. You can actually like get a feel how that will happen. So you can see that tricycle model. The tricycle model in fact we derived in the what you call our own lectures. So now you can actually like put that into a case. So now you can see the vehicle trying to do it, right. So this is a forward wheel drive, and but it is a single wheel. So this is what we have seen. So now what one can actually like see it. So there is a W change, the you can say the further performance will get changed, right. So that is what we are actually like trying to discuss. So what we can actually like see that all the combinations are actually like depend on only one thing, which is what we have actually like derived as a W. So now you change the W, your wheel, you can say scenario or you can say behavior will get changed. So that's why you can actually like say that the non-holonomic and holonomic condition you should know. If the W matrix rank is 3, then you are actually like safe, all 3 states are controllable. So that's what we wanted. So now you recall that particular lecture and see which are the vehicles are actually like you can say holonomic. So those are you can directly substitute what you have derived as a kinematic control. Only thing, if you have more control input and your W plus what you have taken, right, that will optimize the output, or you can say the control inputs, it will optimize. But whereas you have actually like rank of the W is less than 3, then you have to actually like see which are the states you want to control. Then you have to play a small tweak on the, you can say, the position input, which you call desired trajectory, that you have to see. So now what we have done the kinematic control, that too like simulation also we have done along with what you call the wheel configuration. In the next lecture we will see the other class of, you can say, the motion control, what you call dynamic control. Then we will actually like move ahead, further we will bring to the closed loop control along with the dual loop scenario. So with that we will see in the next lecture with the dynamic control. Until then, see you, bye, take care.